Okay. Last time we just started 4.1. We didn't finish it. This is the last section. Excuse me. Chapter 4 is for higher order differential equations. And in the first section, we just discuss some preliminary theory for linear higher order differential equations. Higher order differential equations are hard to solve usually. So we're going to start from the easy ones, the linear equations. And we discussed, the initial value problems and the boundary value problems. And the difference is for initial value problems, the initial conditions are given for 1 point, x equal to x0. For example, the function value y, the derivatives of y are given at 1 point, x0. While for boundary value problems, the condition is given at different points, at least 2 points. For example, for second order differential equations, then you will have initial condition or condition given at x equal to a and x equal to b. Okay. So that's the main difference. And surprisingly, the results, when you try to solve those two types of problems, you will have very different results. For the initial value problems, you can easily find, the solution exists and unique in many cases if the coefficient functions are continuous. All right. Those are a(n)x, a(n minus 1x, and so on, a1x, a0x. This is a theorem we talked about. The only requirement is for those functions, coefficients functions, and g of x, the right side of the equation, to be continuous. Then essentially you can give any initial condition at any point in the domain of the problem, and the initial value problem has a unique solution. So that's some very strong statement, and it essentially tells that the initial value problems have solutions in many cases, and the solution is unique actually. But for boundary value problems, the situation is very different. A boundary value problem can have many solutions, one solution, or no solution. Okay. We just did one example last time. If we just change the boundary condition a little bit, then the solution can be changed dramatically. Okay, so that's a huge difference from initial value problems. All right, so let's just continue with this section, and we want to talk about a homogeneous equation now. Okay. So again, we want to start from the very simple cases, and this time we're going to start from the case where gx is 0. Okay, so the equation just becomes an times dny dx plus a minus 1 times dn minus 1 dx minus 1 dn minus 1 y over dn dx and minus 1 until a1 times dy over dx plus a0 y. But the right hand side is 0. The left hand side is still the same. So this simplified situation quite a bit. And then we try to solve this equation, okay, when the right hand side of the equation is 0. And we call this equation is homogeneous. All right. On the other hand, if the right hand side the equation gx is not always equal to 0, then we call the equation is non-homogeneous. We're going to try to solve homogeneous equations first, and then we can go forward to tackle the non-homogeneous case. Okay. And we're going to introduce the concept of differential operators. This is a very important technique when we do differential equations. We can use the operator theory to handle differential equations conveniently. All right. So what does it mean by differential operator? Let's just denote dy over dx by capital dy. I think we learned this in Car 1. You can denote or write the derivative function in different ways. This is just a different notation. And similarly, we can rewrite the nth derivative of y as capital D to the power ny. Okay. So this D is called the differential operator. So if we just write capital dy, it means you take the first derivative of y with respect to x. Okay. So it's an operator. This D is an operator applying on the function y. All right. Just like some other mathematical operators, And it obviously is easy to show that this operator D is linear. For example, if you try to differentiate C times F, then you can take out the constant C. And so the whole thing just becomes C times D F. Okay. And if you try to differentiate a sum of two functions, then you can obviously take the derivative of each function and sum up. So that means df plus g is equal to df plus dg. So these two properties ensure that the differential operator is linear. All right, any questions? And it turns out this differential operator is very convenient and a powerful tool for us. So based on the differential operator D, we can generate to nth order differential operator. Okay, the capital D is just the first derivative, but then you can write a linear combination of those differential operators, and you just call that L. So let L equals an of x. So that's again the coefficient function for the first term in the differential equation as we had before. And then we just multiply that with capital D to the n. Okay, so remember D to the n is just the nth derivative operator. Okay, and then you just add n minus 1 of x times d to the n minus 1. So d to the n minus 1 is the n minus 1th differential operator, and add until a1 of x times d plus a0x. So this again give us a differential operator. Okay. And the important thing here is you can also show that this generalized nth order differential operator L is also linear. Namely, if you apply this operator L on a linear combination of two functions, namely alpha fx plus beta gx. So L is the operator, alpha and beta are constants, they're not functions. Okay. Then you use the properties of all the d to the n, d minus 1, and so on, and d, they're all linear. So use that property, then you can easily show that L apply on alpha f plus beta y, beta g is equal to alpha times LF plus beta times LG. Okay, so that again means L is linear. All right. So then what's the connection between the differential operator with the differential equation? You can see if you just use the nth order differential operator, you can rewrite the linear nth order differential equation we have before in a simple way as L apply on y equal to g of x. Okay, so you can see the whole equation just simplifies a short notation, but not just that. Okay, so this is just one of the advantages. So we just put all those coefficients and derivatives in one operator, and this operator apply to the function y, and the result is g of x. Okay, so this is the differential equation. All right. Okay, so one of the important results for linear differential equations is called superposition principle. All right. And this applies to homogeneous equations. Remember what it means by homogeneous equation? The homogeneous equation means g equal to 0. So then the differential equation is actually L apply on y equal to 0. Okay. So that's the homogeneous differential equation in nth order. So what does it say about superposition principle on homogeneous equations? It says if you have a bunch of solutions for homogeneous nth order differential equation on n to I, okay, then you can make the linear combination of those solutions, and that will still be a solution for the differential equation. Okay. So if you just write those homogeneous the solutions y1, y2 to yk. So there are k solutions for this homogeneous and all the differential equation. And the linear combination of those solutions you can write as C1 y1 plus C2 y2 plus C3 y3 until at ck yk, where C1, C2, C3 to ck are arbitrary constants. Okay, arbitrary. And you call this the linear combination of those solutions, k solutions. Then that will also be a solution to the differential equation, the homogeneous differential equation. Okay. So let's just look at one example. Well, we have a differential equation here: x cubed y triple prime minus 2xy prime plus 4y equal to 0. And given that the functions y1 equal to x squared and y2 equal to x squared ln x, both are solutions of the homogeneous linear equation. Okay. So we have not discussed how to solve it, but you can easily check this y1, the y2 are indeed solutions to the equation. If we just plug in y1 or y2 in the equation, you can see the equation holds. And those two solutions are valid on the interval from 0 to infinity. That means for all the positive numbers of x. So according to the superposition principle, the linear combination of those two functions, y1 and y2, is also a solution of the equation. Okay. So if you write y equals c1 x squared plus c2 x squared ln x, you get another function, and you can easily check that this function is also a solution to the differential equation if we plug in y into the equation, like we did before. All right. Any questions? Okay, let's talk about another definition. So related to this superposition principle, we have the term linearly dependence. All right. So what does it mean by linear dependence? Okay. So suppose we have n functions, f1, f2, up to fn. So this is a set of functions. Then if you can find some constants, C1, C2, up to Cn, such that when you take the linear combination of those functions with those constants, you get 0. Okay. So C1, F1 plus C2, F2 plus C3, F3 up to Cn, Fn equal to 0. So you're given those functions and you try to find some constants so that this equation holds. Okay, so that the linear combination of those functions with those numbers equal to 0. Then we say those functions, those n functions, are linearly dependent. Okay. So if they exist, or they exist, actually should be exist constants C1, C2 up to Cn, such that this equation holds. All right. So then we say this n functions linearly dependent. All right. The other way to state this fact is that you can actually rewrite or express any function in this set as a linear combination of other functions in this set. All right. So they're linearly dependent. Okay. If the set is functions is not linearly dependent, then we say they are linearly independent. So you cannot express any function in the set as linear combinations of other functions. So that's called a linearly independent. Okay, so let's see some simple examples. In this example, we need to determine whether a given set of functions is linearly independent on the interval from negative infinity to positive infinity or not. Okay, so we got three functions: f1 of x equal to x, and f2 of x equal to x squared, and f3 of x equal to 4x minus 3x squared. So obviously, this set is linearly dependent because you can see f3 is just a linear combination of f1 and f2. Namely, you can express f3 as 4 times f1 minus 3 f2. Okay. Or if you put everything on one side, that means 4 f1 minus 3 f2 minus f3 equals 0. All right, so the set of functions is linearly dependent. Okay, does it make sense? And these are polynomials, as we know. So the domain is all the real numbers, or negative infinity to positive infinity. Okay, so well, how do you know? In general, a set of functions is linearly independent or not? We're going to use determinant or Wronskian. All right. So what does it mean by the Wronskian of the functions? Okay, if you have n functions, f1, f2, up to fn, how do you know those functions are linearly independent? We define, the determinant of the functions and the derivatives up to n-1 order. Okay, so we use W to denote this determinant. It's called the Wronskian of the functions. And this determinant has the entries of all the functions on the first row and all the first derivatives of the functions on the second row, and all the second derivatives of the functions on the third row, and until all the n-1 derivative of the functions on the last row. Okay, so you just compute this determinant, and you're going to get another function. Okay, we call this function Wronskian. Okay, if you learned determinant before, does anybody know what it means by determinant? If you took a linear algebra before, if not, we're going to explain it in the examples later. But we're going to use that to determine, linear dependence or linear independence of functions. Okay, that's from the theorem at the bottom. So let y1, y2, up to yn be n solutions of the homogeneous linear nth order differential equation on the interval I. So we got the n solutions for the homogeneous linear differential equation. Okay. So again, homogeneous means the right-hand side of the equation is 0. So suppose we already found n solutions for that differential equation. Then the set of solutions is linearly independent if the Wronskian of those functions is not equal to 0 for every x in the interval. Okay. So how do you know those n solutions are linearly independent? You do this Wronskian. And if the Wronskian is never 0, then the solutions are linearly independent. Okay. So we got, a lot of definitions and theorem here. But I guess I will do an example first instead of talking about theorems and definitions. Okay, so let's just look at a simple example. Suppose we have a differential equation y double prime minus 9y equal to 0. So this is a homogeneous differential equation in the second order because the right-hand side is equal to 0. And you can easily check that functions y1 equal to e to 3x and y2 equal to e to negative 3x. They are both solutions of the equation. If we plug in y1 or y2 into the equation, you can see the equation holds. And this solution is valid. Those two solutions are valid on the interval from negative infinity to positive infinity. So, x can take any real numbers, that means. So then how do we know these two solutions? So there are two solutions to the differential equation. How do we know these two solutions are linearly independent or not? We can calculate the Wronskian of the two functions, okay? So what you just find the determinant of those two functions and the derivatives. So on the first row, you just put the two functions, e to 3x and e to negative 3x. On the second row, you take the derivative of each function. So when you take the derivative of e to 3x, you're going to get the e to the 3x times the derivative of 3x. So that would be 3. So you get 3 times e to 3x. And similarly, when you take the derivative of e to negative 3x, you get e to the negative 3x times the derivative of negative 3x, which is negative 3. Okay. So that gives you negative 3 times e to the negative 3x. So the determinant of this is just e to the 3x times negative 3 e to the negative 3x minus e to the negative 3x times 3 e to the 3x. Okay, I skip negative sign, second term. So we got the 4 elements or 4 functions. You just multiply the upper left function with the lower right function, subtract the upper right function times the lower left function. Okay, that's how you do it. But then you see e to the 3x and e to the negative 3x, they just cancel, so you get a 1. So in the first term, you get negative 3, and in the second term, you get 3. So at the end, it becomes negative 3 minus 3, which is negative 6. So that's never 0. It's never 0. So according to the theorem, the two functions are linearly independent. Remember, if the Wronskian is never 0, then the two functions are linearly independent. All right. So I guess I'm going to stop here and continue next time. Any questions?